Okay, so we have looked at the small strain tensor, which we had also encountered in our elasticity courses. It's given by this relation, which is a special case of the large strain Green-Lagrange tensor, which is this, or the Almansi tensor, which is this. So the difference is in this cross term, which is neglected for the small strain tensor. Now, let me try to impress upon you through two problems why this distinction is necessary. Let us take a first problem where an element is rotated by an angle theta about the origin. So just imagine we have a, a finite element, which is rotating about the origin, and it takes this orientation where the rotation is by an angle theta. Now, this should not induce any strains, and uh, we will use the small strain tensor to characterize this motion. And the motion is obviously given, it's a pure rotation. So if you take any point x, capital X1, capital X2, it will give you a deformed point, small x1, small x2, which will be related through the rotation tensor. So this is the two-dimensional rotation tensor. Let's call it Q. Now, you write this down, and then the displacements are easily calculated as small x minus capital X, and the displacements u1 and u2 would be this minus capital X1 and this minus capital X2. That's what we have written here. And then the small strain is easy to calculate. Remember, the small strain epsilon 1 is del u1 del capital X1. It doesn't matter whether we write capital X1 or small x1, because the distinction is basically forgotten when you do uh, small strain problems. So let's take the derivative of this, and that derivative would come out to be cos theta minus 1. So epsilon 1 would be cos theta minus 1. Similarly, epsilon 2 would be del u2 del capital X2. That will also come out to be cos theta minus 1. And epsilon 1 which is del u1 del x2 plus del u2 del x1, small strain tensor, this will come out to be 0. Now this is a rigid body motion, and therefore the strains are expected to be all uh, equal to 0. So epsilon 1, epsilon 2, and epsilon 1, 2 are all expected to be 0, but they would only be 0 if if theta is very close to 0. If theta is very close to 0, only then can we expect these two terms to be also 0. Uh, the problem arises because we are using the small strain tensor in a situation which cannot be characterized by the small strain displacement relationships. Okay, now let us reframe this problem in a slightly different way, and um, look at this motion. So here's a motion. So small x1 is alpha capital X1, small x2 is minus beta capital X2 plus gamma x3, and small x3 is gamma capital X2 minus beta capital X3. That's what is given here. Now from this you can easily calculate the F. So remember, Fij is del x, small xi del capital Xj, right? And if you do that, del small x1 capital X1 is alpha, the rest are 0. Then small x2 capital X2 is minus beta, and small x2 capital X3 is minus gamma. Small x3 capital X2 is gamma. Small x3 capital X3 is minus beta. So this is your F. Then we can calculate the Green-Lagrange strain tensor, which is half F transpose F minus I, and this is what we will get. So you have to do this F transpose F, matrix multiplication. You can either do it this way or do it using dyadics. The choice is yours, but in the end, this is what you will get in the Cartesian coordinate system that we have chosen. So these are the components in the Cartesian coordinate system that we have chosen, and these components would be zero if we make the choice that beta is equal to cos theta or minus cos theta, plus minus cos theta, gamma equal to plus minus cos theta, plus minus sin theta. That will make this term equal to 0, this term equal to 0, and then alpha equal to 1. That will make this term equal to 0. So for this choice, let's say, if we take the minus signs, we could have taken the pluses also. But if you take the minus sign for this choice, the strains are, the Green-Lagrange strain is completely equal to 0, which means that this choice should correspond to a rigid body motion where no deformation is taking place, only a rigid body part of the motion is valid. So if we put that, then alpha is 1, so x1 is equal to capital X1. Beta is minus cos theta, so this becomes cos theta x2, and this is minus gamma x3, so this is sine theta capital X3, and this is equal to minus sine theta capital X2 plus cos theta x3. So you can easily see from here that this, with these choices of beta and gamma, this motion is actually a pure rigid body motion about the x1 axis. So that's what is shown here about the x1 axis. This is a pure rigid body motion that it represents, and we already know that rigid body motions can be denoted as a proper orthogonal tensor times capital X plus C. Obviously, in this case, C is equal to 0. There's no translation of the origin, but there's a rotation, and the rotation is given by this. So this is the rotation tensor that governs this rigid body motion. Okay, so so this kind of explains what strain tensor is trying to do. As I have mentioned before, it tries to respond only to deformation. Real strain measure should be 0 for rigid body motions, and should respond only to deformation.